want to thank you all for tuning into our webinar. We're broadcasting here from our location in Logan, Utah. So thank you for coming to our webinar. It's going to be on GNSS and GPS accuracy and how to improve its performance. My name is John Florio. I'm the Geospatial Account Manager here at Juniper Systems. I'm also joined by Brad Thatcher. He's our Marketing Content Specialist who will be moderating for us. In the interest of time, we'll be taking questions offline. So if you have any questions, please enter anything you'd like to ask about in the question box in the control panel in your viewer. All right, let's begin. So today we're going to talk about GPS. And what GPS is about basically is you are here-ish. There's always some debate as to where you really are. So what is GPS? GPS is an acronym for Global Positioning System. It's the first worldwide real-time autonomous positioning system, and it became fully operational in 1995. Originally, it was called NavStar, which stood for Navigation, Satellite, Timing, and Ranging. Its original purpose was to provide navigation for ships at sea. It was built for the U.S. military, specifically to serve the needs of submarines and ballistic ships out in the ocean. But today, it has a much bigger application. We find it in cars, we find it in our little navigation devices when we go hiking and camping. It's used to position drones for delivery and taking aerial images, and of course it's used for land surveying. In fact, GPS can be found in most technology today. It's in every smartphone, it's on top of every cell tower. You can pretty much find it everywhere. Essentially, GPS is a constellation of satellites that orbit the Earth, and each of those satellites has on board atomic clocks. What we are doing is measuring time and expressing time as distance, specifically distances on the Earth. The current GPS constellation consists of 34 satellites. 31 of those are actually healthy and being used today. The baseline architecture or requirements for the constellation is at least 24 satellites. And satellites are launched on a regular schedule. In fact, there was just one launched not too long ago, a couple months ago, by SpaceX on one of their reusable boosters. And you can see here, we have several different generations of satellites up there. The newest one is the Block 3 satellites, which have a lot of new features on them. Now, when you hear someone use the term GNSS instead of GPS, it's a more generic term. GPS is actually one of several global navigation satellite systems. Of course, there's GPS, there's GLONASS, which is operated out of Russia. There's Galileo, which is the European global satellite positioning system. And it's the only civilian-owned system that's out there. And then, of course, China also has a new system called Beta. For purposes of this discussion, we will use GPS and GNSS interchangeably, since most of the systems that are out there, in fact, all the systems that are out there, in some respect or another, work in the same fashion that GPS does. So how does it work? We have an image here that we got from gps.gov, and it's a simple explanation of how the system works. You start out with a constellation of satellites. Each of these satellites is broadcasting radio signals, providing their location in space, the status of the satellite, and the precise time from the onboard atomic clocks. That signal travels through space and through the atmosphere at the speed of light. A GPS device then receives those radio signals and notes their exact time of arrival and uses that time to calculate its distance from each satellite in view or satellites receiving. Once the GPS device knows its distance from at least 4 satellites, it can use geometry to determine its location on the Earth in 3 dimensions. So how accurate is GPS? Well, the 5th edition standard for global positioning, for the global positioning system, the federal standard has the standard positioning surface, which is a surface that all of us use, rated at better than 7.8 meters with 95% horizontal error, and better than 13 meters, 95% vertical error. And the actual performance in space, the signal between satellites, if we were operating outside of the Earth's atmosphere, you would see that over the past year, the average range error or accuracy has been around 52.8 centimeters. So that's quite good. So why is there such a difference between the in-space performance and the standard the federal government expects expects us all to receive with GPS? Well, there's several sources of error. So we're going to discuss those different sources of error, and from there, talk about different strategies to overcome them. So first of all, we're dealing with technology. You have satellites in space and you have receivers on the ground or in an airplane or wherever they're being used. And those are electronic components that have circuit delay, timing issues, various things that you see like on your computer or your smartphone. And those small differences impart tiny amounts of error. But those tiny amounts of error affect time, and that time equates into the error in distance. The GPS receiver has an internal clock and has to match that clock to GPS time. And GPS receiver clocks can vary slightly, so that can be one source of error. Now we'll start in space. In space, you have the satellites orbiting the Earth. To figure out position or timing from these, you need to have a rough idea as to where these satellites are. So you have to have some idea of their orbit. But the orbits that are broadcast from the satellites are a prediction of where those satellites are supposed to be, not necessarily the actual path that they follow, because they're affected by space, gravity, solar wind, things like that. There's also the effect of Doppler shift on the radio signals, and there's just general space geometry. Sometimes your position on the Earth has some satellites close together, or far apart. Some of these errors go away when post-processing, because you're no longer using a broadcast ephemeris, but you're using the observed ephemeris. Okay, let's start diving down. Now we hit the ionosphere. Starting about 600 miles above the Earth and going all the way down to about 46 miles, there is a thick boundary of atmosphere. It's not very dense, but it's very large. And this is the atmosphere being impacted by solar radiation, solar energy. That imparts a charge onto those molecules in space and ionizes the atmosphere. And we can see this when we see the northern lights. Those charged particles are essentially a large electrical static field, and that affects radio signals such as GPS. Diving a little further down, we start hitting the troposphere. Troposphere is the lowest part of the atmosphere. It's the atmosphere that we see and breathe, and it's often filled with clouds, and those clouds are water vapor. Since GPS is broadcast at the microwave frequency range, microwaves are affected by water. So clouds, rain, snow can have an impact on GPS performance. Further down, we get to what's called the lithosphere. That's the Earth we actually live on. There's multipath. Multipath is when a receiver misinterprets a signal that it receives. That signal may be a reflected signal off of another structure or object, and the receiver interprets that as a correct signal. But because that signal has taken not a direct path from the sky to the receiver, but off of another structure or object, that reflected signal is a different time, therefore it traveled a different distance, which equates to an error position on the receiver. Another issue that you have to deal with in GPS, just like multipath, you also have signal mapping. Signal mapping. If you're in a forest, for example, this is what the sky looks like to a GPS receiver. There are parts of the sky that are open and unobstructed, but there are other parts that are blocked by leaves and branches and trunks of trees. Those all interrupt signal and cause delay and affect the performance of your position. And if you're holding your smartphone with a GPS receiver and looking down at it, your human body is also blocking that signal. What all these errors add up to? Looking at all the different error sources that you can experience here on the Earth, you have ionospheric delay. That's the largest source of error. Then you have, of course, the orbital and satellite clock errors, multipath, tropospheric delay, and even receiver noise or clock errors in the receiver. And all those together can add up to over 11 meters of error, or you could be looking at 35 feet of error. Now, there's things that we can do with receivers to cancel out some of those errors. So we're going to talk now about error corrections, different ways of making improvement on those signals. First one we're going to talk about is SBAS. SBAS stands for Satellite-Based Augmentation Systems. It's a form of wide area differential GPS. Based on ground control observations at known reference stations, SBAS is transmitted timing correction signals that are sent over a wide area to correct errors caused by the ionosphere. So its primary purpose is to remove the largest source of error that affects the GPS or GNSS system. They're regional coverage systems that cover specific parts of the Earth. Here's a diagram of WAS, or the Wide Area Augmentation Service system that covers North America. It consists of a series of ground control stations, a master control station, and a ground earth station, which calculates out various error differentials, sends them to a communication satellite, which broadcasts down on the GPS frequency. Here's a schematic of how that works. The ground control stations monitor the ionospheric interference. The master control station then calculates a projected signal delay grid over a wide area. And that's what we're seeing with this dot pattern. The grid is transmitted to SBAS satellites. These are telecommunications satellites that orbit around the equator. And they rebroadcast that information as a GPS message with a special header to indicate that it is an SBAS signal. The receivers apply that signal as a form of time delay to the position calculation the receiver is making, where it is located on the Earth. And that's how you remove that ionospheric error. So here's an example of the various SBAS systems that are available today. We have WAS, which covers North America, EGNOS, the European Geostationary System, which covers most of Europe, again, which covers the Indian subcontinent, and then MSAS, which covers Japan and the Asian Pacific region. There's also a system that was in a test mode for a short period of time that was designed to cover Australia and New Zealand. And that test finished on 31st of July here just recently. And they're looking at the results of that and are planning to bring the system online sometime in 2023. So what about these other parts of the Earth? What about where you can't receive SBAS? Or what if you need some other correction methodology? Well, you can use differential GPS. And this can be real-time or post-processed. Differential GPS is a system to provide positional corrections to the GPS signals and to your position. It uses a fixed known position to adjust the time signals for the unknown or roving position, which is the person standing there with the receiver. And this eliminates pseudo-range errors. Another method that's out there is called PPP. Sometimes you'll hear about this. It's precise point positioning. It's a method where a single receiver can actually calculate an accurate position by tracking continuous GPS signals for an extended period of time. Now, the time required to calculate the position is called convergence time. And this is true that a receiver that's capable of doing this over a period of time. If you look at this graph, the X scale shows time in seconds. And when you get out to about what's equivalent to about 20, 25 minutes, you're getting a very reasonable position of maybe 0.2 of a meter. This can be done standalone by receivers, or it can be done using an L-band external correction source. So the L-band systems that are out there often have this convergence time issue to deal with because they're providing a worldwide broadcast over L-band satellites. And that is compared to what the receiver is receiving and converging to a good position solution. Another method that's out there that's very popular is RTK, or real-time kinematic. This is a method of obtaining real-time moving accurate positions. It's based on calculated vectors between a base and a rover receiver, or a network of bases and a rover receiver. It requires a known position or known positions in the solution, and also requires carrier phase tracking. So not only looking at the information in the GPS satellite transmission or signal or carrier, but also measuring the carrier frequencies themselves to compare between the base and the rover carrier frequencies and determine a position on the Earth. Typically, it's done with dual frequency receivers. It can be done with single frequency, but it's a very fragile solution. It's not a very reliable methodology because you don't have two different frequencies to compare against each other. It also takes more time. Now, along with RTK, you need to have a way of getting the base information to the rover. And the most popular method now out there, traditionally they used to use line of sight radio or just out of line of sight radio. And today we're using a lot of places using NTRIP. Now, NTRIP stands for Network Transport of RTCM via Internet Protocol. NTRIP does not mean RTK. NTRIP means RTCM, which is one of the correction formats used in RTK, transmitted over the internet. So this is where someone can use their cell phone or a Wi-Fi hotspot and connect that to a GPS receiver to get an RTK or a real-time differential solution. This image here is an example of what a network looks like. This is the network for Utah. So the different correction types we talked about, there's strengths and weaknesses in each of these. They can all achieve similar levels of accuracy. Some can achieve more accuracy depending upon how much data you capture, how long you capture data, or the quality of the solution that's being calculated. RTK, of course, can get you down to the centimeter. Post-processing can also get you to similar accuracies depending upon what type of data is being processed. We have SBAS, comes at no cost, gives you wide area coverage, but it's regional, not global. And because the satellites are geostationary, the satellite can be blocked. In other words, if you're in the northern hemisphere and you stand on the north side of a tree, you could be blocking the signal coming from a satellite on the equator, which would be in the southern sky. PPP, it doesn't require any additional equipment, no additional signals required, but it takes a long time to converge. And any interruptions to that signal can extend that convergence time. So realistically, most PPP applications are stationary locations for receivers. In fact, cell towers all have receivers on top of them that perform PPP solutions because they need the timing for your cell towers. Real-time differential GNSS, this will give you increased accuracy. It removes a lot of the error sources, ionosphere and troposphere, for example, but it requires additional equipment. It requires radio links or some connection between multiple receivers, so increased system cost. Now you can use post-processed differential GNSS. This will give you the same amount of accuracy. It is referenced to a known local control, but it can't perform real-time tasks. It's kind of like the old days of developing 35mm film. You can take a great picture, but you don't know if it's a good picture until after you've developed it, until after you process the data. RTK, of course, will give you the highest possible accuracy for a real-time system, but it does come at a higher cost, and it requires multiple receivers or a network, and it's a more complex workflow. So there's strengths and weaknesses to all these systems. You just have to choose based upon what type of work you're trying to perform. So let's take a look at what kind of performance you might see from different corrections that are out there. And for that comparison, we're going to use an example. We're going to use our GNS2 receiver. Now this is a real-time single frequency sub-meter GNSS receiver. It's a standalone receiver. It's all in one. It includes the receiver engine, the main electronics and communications board, the battery, the antenna. Everything's all self-contained in a rugged housing. It's capable of achieving 30 centimeters horizontal accuracy with an SBAS solution. It uses SBAS as its primary correction source, but it can also be used with NTRIP for corrections using the RTCM signal. It can also be post-processed. So here's an example of a geode receiver sitting just outside of our building. What we did is we actually took this on the patio of our building here and turned it on and just started collecting 30 minutes of autonomous, uncorrected GNSS data. You'll see that there's some blocking of signal because we're up on the roof and we're near another part of the building. But on the vertical scale, we've got plus or minus 0.4 meters. On the horizontal scale, plus or minus 0.6 meters. So we're getting a pretty good, respectable position. Not bad for a receiver, but a lot of people want better than that. All right, now we switch over and turn on SBAS capability. And here's 30 minutes of SBAS data. And you'll notice it falls pretty much within that 0.2 meters in every direction, maybe a little bit further out. So the end solution here is about 0.2, 0.3 meters. If we take that exact same receiver in the exact same location and then connected it to the local Utah reference network and collect 30 minutes of data, we get a slightly better solution once again. And when we calculated and averaged out this data, this was about 0.2 meters of accuracy. So it was a little bit better than the SBAS data, which makes sense because we're getting a solution from a nearby correction source as opposed to a wide area average correction source, which primarily only addresses the ionosphere. Okay, what about post-processing? So here's a set of data that was collected with SBAS. Once again, we took out and captured a number of points with the receiver and just used the SBAS corrections that were available. And you'll notice that 93% of those fell within a 1 foot radius circle. That's pretty good. The root mean standard error was 0.309 meters. So basically a foot in any direction. What about the vertical? Our vertical error was up or down about 1.5 feet. We came up with a root mean standard error of 0.444. And if we use the National Spatial Data Standards to calculate this, we get 0.769 meters. So about 1.5 times the horizontal. So as a good rule of thumb, your vertical position is about 1.5 times your horizontal position. Now we took that same data and post-processed it against the base station. It was about 13 miles away. All that data processed to within about a 6-inch area. See, that data looks pretty good right here. In fact, that little orange box on the screen, that's the same physical size as the geode receiver. So this was a case of getting very good data. And this is what you can observe potentially even with a single frequency system if you post-process. What about the vertical? This is kind of interesting. The vertical data actually looks better than the horizontal. Now you have to remember though, this is processed to a single base station, so a single baseline solution. So you have to assume that there could be some bias. If I wanted to have a better idea of how good the vertical position was here, I would want to compare this against multiple base stations. So that's all in good looking at static data, capturing points. What about dynamic data? What about moving around? Well, the red line you're seeing on the map here, this is data captured with my smartphone. In fact, I was using an iPhone in this instance. And you can see I was up about as much as 30, 35 feet at times off of the track. I was simply walking around a sidewalk. The blue line was the geode receiver receiving SBAS data. And when I did the calculations on that data, it came into about 30 centimeters RMS. And the green line was the results that I received using NTRIP as a correction source. And it came in a little bit better. It was closer to that 20 centimeter accuracy range. Now you'll notice that the blue and the green are offset, and this is another source of error that we find many people really run into this as the biggest source of error in what they're doing with data capture with GPS or GNSS, and that is they have a projection error. The NTRIP data is based on NAD83 here in the United States, North American data of 1983, whereas a GPS signal is essentially based off of the WGS84 datum. So dealing with those datums and those projections is a big issue you have to plan for when using GPS. In fact, we can conduct an entire webinar just on that subject. So I talked about what a receiver can do. What about some best practices in the field? Now, first things first, you want to set up your receiver properly. And I can't stress how many times, and we will all do this once in our life, we'll forget to charge a battery somewhere. We pick up our phone and darn, the battery needs to be charged. You want to make sure you charge the receiver and charge the data logger. Both components in your system have to be charged. You want to make sure you establish communications. Make sure that the receiver is connected properly to the data collection or data logging device. Then power on your receiver. Make sure that the receiver is up and running before you do anything else, so you can give the receiver a chance to establish a good position. Now you also want to make sure you check your receiver settings. Things like the data stream message coming out of the receiver. In the case of a mapping receiver, often you're dealing with the NMEA format. And you want to make sure you at least have the GGA and RMC messages. Those are two formats or types of messages that are needed for software to determine what the GPS position is. You want to make sure that the message update rate is configured properly. Are you capturing data at a slow rate where you're walking or standing still, or are you trying to capture data very fast in a vehicle? And you want to make sure you configure the data output precision. You don't want to be trying to capture a precise sub-meter or better position, but have your data output in, say, only 4 or 5 digits to the right of the decimal point, because then you won't have all the information you need to have an accurate position. Other things you want to do. You want to deal with receiver behavior, like make sure the antenna mask angle is set correctly. So the antenna mask angle is a setting that will allow you to turn off or tell the receiver to reject GPS satellite data below a certain angle above the horizon. Signals that are coming in very low on the horizon experience a lot of error. They're exposed to a lot of atmosphere, a lot of things that can reflect off it. So you want to reject those from your solution. And of course, you also want to make sure you configure a correction method. Are you using SBAS? Are you connected to an N-trip caster? You want to make sure you have those settings all set up properly. Now you got your receiver up and running, but how do you carry the thing? How do you move around with this? You know, someone will sell you a GPS receiver or a GNSS receiver, but you need some way of using it in the field. Well, a traditional method is you might put it on a standard surveying range pole. You can use a fixed height pole or you can use an adjustable height pole. Just be careful with those adjustable height poles that you don't change that height without recording those height changes in your software, or else you can have some issues with your elevations. Another approach you could take, if you want to have something on a pole, in other words, to force the operator to hold it over a specific point, but you're not so concerned about the elevation, you're not so concerned about the pole height, is you can get something like this. This is a camera monopod. This is used for stabilizing cameras. They can also be used to stabilize a GPS receiver. They're collapsible, they're inexpensive. They can even be put into a backpack to be used as a ad hoc backpack pole. Or you can go with a traditional backpack setup where you have the receiver mounted in the backpack and of course extended above your head. In some instances, you might be working in rough terrain and you want to protect that receiver because the receiver is the more expensive part of the solution. So you can connect an external antenna and just put a little patch antenna up on your shoulder. Some people might even stick it up on a hat or a helmet or something like that. Here's a neat little solution we found that a lot of folks like. We found a mount that you can attach to any backpack strap, and that mount can attach to the bottom of the geode receiver and have it sitting right next to you at a common location right over your shoulder. And it doesn't require any cables or any wiring. You don't have to worry about connections, things like that. You just have your wireless connection to your data controller. If you're on a vehicle, say maybe you're going to be mapping with an ATV, you can get some clamps and mounts and attach it to various roll bars on the device. You can even use the receiver in a handheld configuration. You can mount it to a tray and carry it all in your hand along with a smartphone. So there's lots of different ways to transport a receiver and data capture, data collection system. You have to choose the one that's going to be best for you in the field. Okay, lastly, we're going to talk about field mapping techniques. This is some good procedures to follow and some of those not so good procedures, things you want to watch out for. So we'll start with the classic example. In the mapping world, I don't know how many years I've been doing this, but everyone has always done the demonstration of mapping a fire hydrant. I haven't really ran into too many people who need to actually do that job, but it's a simple object that's easy to find and great for training. So here you see me standing with our geode, and I'm using it in a handheld mounting tray with a smartphone. But everything looks fine, looks like nice open sky, open area to capture some positions, but really, this pie piece, let's think of this in 3 dimensions, this represents the space that the satellite signals are traveling through to get to that receiver and that antenna on the top of the receiver. Now where I'm standing, my body is actually blocking some of that signal. So while handheld can be convenient, it can also impact your positioning accuracy or solution. Another approach might be to put it on top of a pole. Well, this is good because we've gotten the receiver higher up into the sky, we've exposed more sky. You don't have anything blocking it nearby. The only thing I would say is from a safety standpoint, if I wanted to map this hydrant, I wouldn't stand in the road where traffic might be coming. I'd stand over here on the side of the road where it's a safer position. All right. Many people need to map footprints of buildings or structures. And the tendency or urge or desire is to just go out there with a receiver and let's just go up to the corner of the building and capture each building corner. Well, that presents a problem. In this position, we are blocking almost 25% of the signal that satellite receiver is going to pick up. Likewise, we're right up against a large flat surface where signal can reflect, creating multipath error. This would be a bad place to actually measure, regardless of what receiver you're using, regardless of the technology or manufacturer. It's just not a good practice to follow. A better approach would be to step back. You want to step back from that building corner. You want to take a offset measurement. This is where laser rangefinders come into play. It turns out if you were to do a survey of mapping that's done out there, almost 25 to 30% of mapping that's done can be done more effectively with offset measurements. It requires a user to think three-dimensionally. You have to think a little bit about where you are and how you're going to capture information. Sometimes you have to use additional tools like a laser rangefinder, but by doing that, you can improve your overall positional accuracy for your GPS position and then get a linear distance offset from the wall to your receiver. A good rule of thumb to follow with structures is you want your receiver to be twice the distance from the obstruction as the height of the obstruction itself. If you're that far away, you're not going to be blocking very much sky. You're probably not going to have a multipath issue. Now, it may not be realistic in all applications, but it's a good rule of thumb to follow. Let's look at this example here. In this example, I had to map this curb line. Well, the problem is there are vehicles parked on the curb line, so I used my software and I took a point over here and I paused my position. Then I walked over to the other side of the vehicle and captured another point and continued that line, so I have a nice clean line of my data. But again, we have a problem. It looks like we're okay because we don't have any obstructions on the antenna, but we're right next to this big metal object, this truck, which is a great reflector for GNSS signals and can be a source of multipath. Having the receiver higher up than the vehicle gives me some good multipath rejection, but if I was using a receiver down here by my hands with a handheld, that signal might be reflecting off the vehicle and I can get a significant error in my position. You have to think about structures three-dimensionally again. Think about things around you. The worst place in the world I would want to be mapping is right downtown Manhattan, where I'm next to all these tall buildings covered with metallized reflective glass. This has to be a GPS nightmare. What about trees? There's people that want to map trees. Right? Trees are important. Well, one option is you can get that antenna above the tree, but sometimes the trees are a couple hundred feet high, so you don't really have a pole that's going to be able to get that antenna above the tree. And regardless of the manufacturer, the make of the product, or the technology applied, putting a receiver under a tree is going to cause error. It's going to induce positional error in your signal because you can't account for all those leaves and all those branches and all that water stored in the tree. There's another approach you can take, using geometry as your friend. Now, it's very common to want to map the drip line of a tree. So what you could do is you could capture a position on one side of a tree and capture the position on the other side of the tree, getting better GNSS signal in both instances on your receiver, and then apply a little geometry in your software. You simply draw a circle from each point, and where those two circles intersect, the tree has to be in that location. What about this example? This is a much better environment, right? The receiver is high up above me. It's a wide open field, no obstructions around me. Everything should be fine, except I'm standing under a power line. Power lines, if you've been near high tension, high voltage power lines, you'll hear them crackling and hissing sometimes. That's air ionizing around that power pole. Now, that ionized air is, again, charged particles, and that can influence GPS signals. In the case of a simple mapping project where my position is only 1 to 2 feet or so, I'm not going to be so worried or so affected by that. In the case of this example, there's probably not a lot of power, so not a lot of noise being created. But if I was using an RTK receiver, I was near a high voltage line, I could be seeing some error induced on my signal. Likewise, that noise can affect not only the GPS receiver, but could be affecting things like the radio system you're using. All right, one more example. Here we are. I'm just going to map this pole. Very simple. Okay, I'm up against the pole, so I'm blocking some of the signal, but generally I'm exposed to sky. Everything should be fine. But I'm under the building. Moral of the story is pay attention to your environment. Think three-dimensionally. Look around you. Watch out for what can be affecting your signal. And if you pay attention to your procedures in the field, those are going to be just as important as the technology in your receiver and how you use it. All right, summary. GNSS, or GPS, is a worldwide, highly accurate positioning system. There are error sources that exist, but they can be largely solved through the application of good technology and good field practice. You want to choose the technology and the correction methodology that's suitable for the data quality that's needed. You may not need to use RTK if you're only concerned about mapping simple objects or temporary objects that are going to get moved later. You can use a simple mapping product, but you might not want to use that if you're going to be laying out stakes and boundary for a piece of property. So just make the right choice. You want to make sure you configure the receiver and the software as needed prior to going to the field. There's nothing worse than having to go out to the field, turn around, go back and get the battery you forgot, drive back out to the field, turn on the receiver, and then discover you don't have the receiver configured correctly. You want to approach your field work with a three-dimensional view of the world. Think of obstructions. Think of things that will impact the receiver around you in all directions, above you, near you, that type of thing. Lastly, practice your art safely. You're out there working. It's a science and an art. There's science involved, which is the math the receiver does. There's art, which is the art of the skill of the data collector, the person capturing data. Use sunscreen. Wear a hat. Put on sunglasses. Make sure you drink plenty of water. Be visible. Have a vest on to protect you. Allow others to see what you're doing. And these modern times, you probably want to wear a mask too. So that's it. Well, thank you for participating. Here's some references. I would highly recommend you go to gps.gov if you want to learn more about the GPS system. Also, the European system has a site called Navipedia, which has some great information on all the different GNSS systems that are out there. And thank you very much for attending.